results from Serre's GAGA. But I will try to do it. So I will try to go fast and finish all this topic, this class. Let's see. Okay, so let X be a complex algebraic variety. So the first thing that we have to do is to note that to every complex algebraic variety we can associate a complex analytic variety. Okay. So we can associate a natural structure of analytic variety xn. I will denote it like this, xn, in the following way. So for every open affine set, open set, U contained in X, we know that we have here an isomorphism of U by definition with some complex algebraic subvariety of some Cn, right? This is a algebraic subvariety. Well, maybe I will write it like this. So this is an algebraic isomorphism. This is an homeomorphism in the Zariski topology. And B is given by the zero locus of some polynomials inside some Cn, right? Okay, so since this B is an algebraic subvariety of Cn, it is the zero locus of a finite collection of polynomials. These polynomials are in particular holomorphic functions, and so this B has a natural structure of analytic subvariety of Cn. Right? And note that, well, in order to have an analytic structure, B has the induced topology by Cn, but the topology by Cn as an analytic variety. So it is the Euclidean topology in Cn induces a topology in B. This topology is different from its Zariski topology. It's much bigger. It has these small open sets. And using this bijection that we have here, we can transport the Euclidean topology, the analytic topology of B, to a topology on U, right? So in every open affine set, we have a topology that is bigger than the Zariski topology of U. And, well, on every open affine set, we induce this topology. We can show, so using this bijection, we can induce an analytic structure and topology on U. And it can be shown that these structures are compatible and induce a natural analytic structure on X. Okay, so it induces a topology on X that is not the same topology that it had originally, and will be in fact the Zariski topology whenever X is a affine variety or projective variety. Is what it has to be. I mean, not the Zariski, I mean the analytic topology induced by the bigger space. Okay. Okay, so we have this analytic structure induced on every complex algebraic variety, and furthermore, for any OX module F, we have an induced analytic sheaf. And we denote Fn, that is over Xn, over the analytic topology of X. Okay, and how it is defined? And it's given by, so in order to define the sheaf, we will just think of it as an étale space. So we will just define it, we will just define the stalks. So Fxn is by definition the stalk of F at X extended by analytic functions. Okay, for every X in X, right? So in some small neighborhood, Fn, the section of Fn in this small neighborhood will be a collection of germs of algebraic sections of F multiplied by analytic functions on X, and such that they are compatible, right? Whenever you look at this section times this holomorphic function in some small neighborhood, and you restrict it to the other points inside this neighborhood, you will get the other sections that you are taking here. Okay. This is by definition the analytification, the induced analytic sheaf of an algebraic sheaf over X. Okay. So it's a space generated by algebraic sections times holomorphic functions. We're extending the coefficients. Okay, so what we'll explore, I mean, what Serre's GAGA correspondence explores is this correspondence, this functor, right? The functor that takes some algebraic sheaf and gives you an analytic sheaf. How is this correspondence? And we will, and what we will prove is that this is a nice correspondence in the case where X is a projective algebraic variety. Okay. So well, this example is trivial, but so the analytification of the structure sheaf is this. This is obvious. But you have to keep in mind this. So the first result that I won't prove completely, I will just give the sketch of the proof. It's the following. So let X be a complex algebraic variety. Then for every x in x, OXN x is a flat OXX module. Okay, this is a very important result, purely of commutative algebra. Okay, so the idea of the proof. Okay, so first of all, we can assume x is affine, and x is given by the zero set of some polynomials. Okay, inside some Cn. And we can assume x is 0. Okay. So in this case, what are these rings? So OXN x is exactly the ring of convergent series in n variables mod the ideal generated by the germ of analytic subvariety of x at 0, right? And on the other hand, we have the algebraic ring of regular functions. Is exactly the ring of regular functions, that is by definition this ring, localized at this maximal idea corresponding to 0, that is just this idea. Okay. Okay, so passing to the completions. I mean, both rings are local rings, so they have completions. So we will get that the completion of the regular functions is exactly the ring of formal power series mod the ideal generated by x. And the completion of the analytic ring is the same ring of formal power series, but now divided by the ideal generated of the analytic by the analytic germ of variety of x at 0. Like this, right? So what I want to prove first is that these two rings are in fact the same. Okay, so in order to prove that they are the same, that OXX hat is OXN x hat, we just need to check it is enough to prove that these ideals are the same, and in order to prove that they are the same at the level of a formal power series, it is enough to prove that they are the same in a smaller ring, that is the ring of convergent power series. So it is enough to prove that this equality is true. Okay, and well, and this is not we are not so far from this, because we know that we have the analytic Null-Stellensatz theorem. The analytic Null-Stellensatz theorem tells you that in fact this ideal is radical, and in order to prove that the radical of this ideal is exactly this, we just need to check that the germs of analytic varieties that they define at the point 0 are the same, and that's true, right? So we have this equality, right? So the only thing that we have to prove is that this ideal is reduced. I mean, it's radical, right? So it is enough to prove this, and so it is enough. So by the analytic Null-Stellensatz, it is enough to show that this ideal remains radical when you extend it to the ring of convergent power series. Okay. Well, this fact is not that easy. In fact, in Serre's article, he cites Chevalier. Okay, so let's try to prove this. I mean, I will just give a reference for this. Okay. So let F be a convergent power series such that f to the k belongs to this ideal. Okay, we want to prove that f belongs to this ideal. So we know that X has a finite number of components, and so the ideal is the intersection of this its finite primary decomposition. In fact, since this ideal is radical, these primes, I mean these primary ideals are in fact primes, and they correspond to the components of X, right? So we will have that this OXX check hat is exactly it is contained inside. So let's say that X1 Xi is the zero set of Pi, right? Are the components. So there is a natural inclusion of this completion inside these other completions, in the product of these completions. And for all, I don't know. Okay. You can take here just the components passing through X. Okay. So we have this natural inclusion, and so in order to prove that this ring is reduced, we just need to prove that each of these rings are reduced. Okay. If we prove that each of these rings are reduced, we get that this one is reduced. Okay, and how we will prove this? I mean, this is difficult. So all these OXI X hat are reduced since these rings OXIX are, in fact, that these guys are reduced is exactly the same as this ring being analytically unramified. Okay, and why are these rings analytically unramified? Since they are since they are exactly Noetherian, Nagata domains. Okay, so I won't give you the definition or the proof of this. So the reference for all these results and the definition of Nagata ring is the Stacks project. Stacks project. So look for the section 10.157. The lemmas 6, 13, and the propositions 15 and 16. Okay, so well, this fact means that the completion is reduced. Okay, so in particular, we have that F. Well, we know that Fk belongs to this ideal, right? Times C x1 to xn, and since this ideal we know it's radical by this fact, we get that F belongs to this ideal, and also it is inside the ring of form of convergent power series, and this is exactly this ideal, right? Okay, and so this, I mean, the reducedness of this ring implies the reducedness of the radicalness of this ideal. Okay, and so we conclude that in fact these two completions are the same. Okay, so now we want to prove that OXN X is flat as an OX module. So in order to prove flatness, we just need to prove it for a finitely generated ideal. So let I contained, well, injected in OXX be an ideal, right? Okay, since we know that X is an algebraic variety, OXX is Noetherian, and so this ideal is finitely generated, right? So consider an inclusion. We have to check that. We have to prove that it remains injective when we extend it by analytic functions, right? So suppose it is not injective, not necessarily, and take the kernel. Okay, so take n be the kernel of this extension of this morphism, and so we know since the completion is flat, we know that n tensor over OXN x tensor with the completion, it will be 0, right? But this is exactly the same as the completion of n as an OXN module, right? And so since everything here is Noetherian, I mean OXN is also an Noetherian. This is finally generated. This n is also an Noetherian module. We know that n is extended, is inside n hat, right? And so n is 0. Okay? This is the proof. Clear? Okay, so a corollary of this theorem is that the functor is exact and sends a coherent sheaves to coherent sheaves. Okay, is this clear? I mean, it's clearly exact, since in order to prove that an sequence of a morphism of OXN modules is exact, you just need to check it on the stalks. And so it's clear. And the coherence is something that you again check from an exact sequence locally. And the exactness of this sequence also is something that you check in the stalks. Okay, so this is clear. Okay, so now I will prove the first part of GAGA theorem. So GAGA 1, let X be a projective algebraic variety, and F an algebraic coherent sheaf over X. Then we have a natural isomorphism for every Q where this morphism is given in check cohomology in the natural way. For U any affine open covering of X, right? So it is good with respect to F and Fn by Serre's and Serre's theorem and the fact they are time. Okay, this is the first part of GAGA. So is it clear? Is it clear what is the morphism epsilon? It's just the inclusion on the sections of algebraic sections, looking at them as analytic sections, okay, for each intersection of open sets. Okay, clear? So the proof. Okay, so the first claim. Claim 1. So GAGA 1, the theorem is true for x equal to Pn and F, the structure sheaf. Okay, this is the first thing we will prove. And the proof is trivial, and so in fact, so for q equal to 0, this is just the constant functions and in both sides, right? This is trivial, okay? I mean, holomorphic functions define projective varieties. They are always constant, and also the algebraic functions, okay? But they will be holomorphic. And for Q, we already know, right? HQ of x OX. I mean, this is Pn, right? We already compute these groups. They are all 0. For Q bigger than 0, we proved it in the previous class. And in the analytic side, this is exactly by Dolbeault theorem. These are the 0Q groups of Pn, and we know which are the cohomology groups of Pn, the Rham cohomology group of Pn, and so by the Hodge decomposition, we know these are all 0, right? Okay, so this is for Q bigger than 0. So we know that GAGA is true for Pn and the structure sheaf. So the claim 2 is that GAGA is true for x equal to Pn and F, the twisted sheaf. Okay, and when this is true, so we proceed by induction on n. So consider the following short exact sequence: O Pn m minus 1, O Pn m. This is the, let's say, so take Pn minus 1 to be the 0 set of xn equal to 0 inside Pn. So this is the multiplication by xn. And here we have the structure sheaf of, so let's say that this is I, the structure sheaf of Pn minus 1. Okay, so we have this short exact sequence associated to the subvariety Pn minus 1 inside Pn. And so taking the long exact sequences, we will get the following diagram. So we have here HQ minus 1 of Pn, O Pn M, HQ Pn O Pn. Now this is Pn minus 1, Pn minus 1, Pn M minus 1. And here we have, I will need more space, sorry. From here. So HQ minus 1, Pn minus 1, O Pn minus 1, M, HQ, Pn, O Pn, M minus 1, HQ, Pn, O Pn, M, and HQ, Pn minus 1, O Pn minus 1, M, and so on. Okay, so we have this long exact sequence, and we also have these morphisms, right? These analytifications, I don't know, these epsilon morphisms. So you have the same thing here, but in the analytic side. Right, so we have these morphisms here. Okay, so by induction we know that this is an isomorphism and this is an isomorphism, right? And we want to prove that, so let's call this map epsilon m minus 1, and this is epsilon m. And so we know by Five's lemma, by 5 lemma, epsilon m is an isomorphism for every q if and only if epsilon m minus 1 is an isomorphism for every q. Okay, so since by claim 1 epsilon 0 is an isomorphism for every q, we are done, right? Right? This proves that epsilon m is true for every m integer, right? So this is the claim 2. Now claim 3. The claim 3 is trivial. Is if GAGA 1 is true for x equal to Pn, then it is true. Okay, and the reduction is the same as always. So if x is contained in Pn, let's say that the inclusion is I, and F is algebraic coherent over X, then E star of F is algebraic coherent over Pn, right? And the analytification of the push forward is exactly the push forward of the analytification. Okay, so this is trivial. And so we have reduced GAGA 1 to prove it for Pn. And we have already proved it for some kind of sheaves, for the twisted sheaves. Okay, so let x be equal to Pn. And we know by Serre's theorem, by one of the theorems proved by Serre, and that we saw in the previous class, we know that we can write f as a quotient of a finite sum of twisted sheaves, right? Where G is coherent and F and L is a finite sum of twisted sheaves. Right, and so we have the following diagram. So we have here, so what's the first one? So we have this diagram. Okay, HQ, Pn, G to HQ, Pn L, HQ, Pn F, HQ plus 1, Pn G, HQ plus 1, Pn L, and so on. Here we have the analytification maps, HQ, Pn, Gn, HQ, Pn, Ln, HQ, Pn, Gn, HQ plus 1, and no, this is Fn, Pn, Gn, and HQ plus 1, Pn, Ln. Okay, we have all these maps. We have this diagram, and we know by the claims that this is an isomorphism, and this is also an isomorphism. Right? So let's call this map epsilon 1, epsilon 2, and epsilon 3. Okay, so the first thing that we will prove is that in fact this map epsilon is not an isomorphism. No, it's not an isomorphism. We will prove it is a surjective map. Okay, so let's prove that this map is always surjective. And we will do this by induction, by decreasing induction on Q. Okay, so we know that this is trivially true for Q. This is trivial for Q bigger than the dimension, right? Since both groups are 0. Right, and so by induction, we will have that epsilon 3 is surjective. Right, this will be true by induction, and so we can conclude that epsilon 2 is surjective. Just using this part of the diagram, if we have this kind of diagram, and this map is surjective, then this map must be surjective. It's just diagram chasing. Okay, so this proves the induction of this claim. And so, well, this is true. So since epsilon 3 is surjective, by induction hypothesis, we claim that we conclude that epsilon 2 is surjective, and so this is true. I mean, epsilon is surjective for every q. Right? In particular, we know that epsilon 1, epsilon 2, and epsilon 3 are surjective. Okay? And so now we will prove by induction by decreasing induction on Q that epsilon is in fact an isomorphism. Okay, so now we know that all these maps are surjective, and we know that by induction this is also an isomorphism, right? And so this is enough in order to apply the 5 lemma and conclude that epsilon 2 is injective, and so it's a bijection. Choose epsilon 1, epsilon 2 are surjective, epsilon 3 is an iso by induction hypothesis, and so by 5's lemma epsilon 2 is an isomorphism. And this finished the proof. Okay? So this is the first part of GAGA correspondence. Do you have questions? Clear? Okay, so GAGA 2. The second part of GAGA is the following. So let X be a projective algebraic variety and F and G be two algebraic coherent sheaves over X. Okay, then for every analytic morphism G, there exists a unique up to isomorphism no, it's unique. There exists a unique algebraic morphism such that the analytification of this morphism is G. Okay. So let's prove this. Let's prove. So consider A to be the sheaf of homomorphisms. This is the sheaf homomorphism of OX modules from F to G. Right? This sheaf is defined like this. So in every open set, it is just the set, the group of sheaf homomorphisms of OX restricted to U modules from F restricted to U to G restricted to U. Okay, this is a sheaf. In fact, this is a coherent sheaf. So since for every pair of finitely generated A modules, for every pair, let's say M and N of finitely generated A modules over an Ethereum ring, this A module, the home, it's also finitely generated. We conclude that this sheaf is coherent. Okay, and furthermore, for every x in X, we have that the stalk can be identified with this set of homomorphisms of sheaves over the local ring, right? Okay, so we have this fact. So in particular, for every element of the stalk, F in AX, we have an induced analytification of this Fn that will belong to a set of homomorphisms of OXNX modules right? This is just by extension by holomorphic functions, right? And so we have a morphism here that goes from A to B, where B is defined as the sheaf of homomorphism now of OXN modules from Fn to Gn, right? And this sheaf is over the analytic topology of X, right? So we cannot have a morphism from A with respect to the algebraic topology. So here we will put A prime, where A prime X is exactly the same as AX for every X in X, but A prime is a sheaf over Xn, right? So in particular, this A prime is nothing else than the J inverse of A, where J is the map, the continuous map from Xn to X, right? The identity map. Okay. So we have this morphism, and in fact, this is an OX prime morphism. right? Where again, OX prime is J inverse of OX. Okay, so in particular, extending this morphism to an OXN morphism, we will get that we have a natural map from AN to B, right? Say phi. Okay, and we claim phi is an isomorphism of OXN modulus. Okay. So how we'll prove this? It is enough to prove it in the stalks. So in fact, it is enough to prove for every x in x that the map in the stalk is an isomorphism, right? X, this is exactly the home of OXX from Fx to Gx tensor as an OXX module with OXXN. This map to the home of OXNX Fnx Gx is an isomorphism. To prove that this is an iso. So in order to prove this, consider a sequence, an exact sequence of the following form: OX x to the m, OXX to the r, Fx 0, right? We know we have this since F is coherent. And so since tensoring with the analytic functions it remains exact since it is flat, and so since this thing is flat and the functor home is left exact, we will get the following diagram with exact rows. Okay, so we have this here, and downstairs we have the other thing. We have these maps. Okay, and and these two maps are clearly isomorphisms. In fact, this is gx to the r, and this is gx and to the r, right? The m, and this one is gx to the m. Okay, so these are isomorphisms, and so this one is an iso. So what we want to prove is that we just need to know that what we want to show is exactly this, that the global sections of A, this is exactly a morphism between a sheaf between F and G, right? So here we have the global sections of Xn, An, and here we have the global sections of Xn and B, right? We want to show that this composition is an isomorphism, right? And we already proved that this map here, this is phi, is an isomorphism of sheaves. So obviously it will be an isomorphism of global section. And this is exactly epsilon, the map given by GAGA 1. So this is an isomorphism by GAGA 1. This is an isomorphism by what we already proved, and so we're done. Okay. So what time is it? Okay, so the last part of GAGA is the following. It's GAGA 3. So let X be a projective algebraic variety, and then for every analytic coherent sheaf G over Xn, there exists a unique up to isomorphism algebraic coherent sheaf F over X such that Fn is isomorphic to G. Okay, so before proving this theorem, I will do some remarks. So remark 1 is that the uniqueness follows from GAGA 2. Okay, in fact, given F1 and F2 such that F1 and is isomorphic to F2 and under some isomorphism G, we know that there exists some morphism between F1 and F2, some F, such that Fn is equal to G. right? And so if we write down the kernel and the co-kernel, we know that if we, so this is F. If we tensor by, if we apply the analytification functor, we will get also an exact sequence here. And since G is an isomorphism, this implies that this is 0, right? And so, well, since these two sheaves are coherent, this implies that H and G must be 0, right? So since H and G are coherent, we will have that for every x in X, this Hx is inside Hx hat, the completion, and this is exactly Hxn tensor over Oxnx with Oxxn the completion, and this is 0, right? And the same thing will happen for Gx. Right, and so H and G are 0, and so F is an iso. This is the first remark. The second remark is that we can reduce ourselves to the case where X is the projective space. On the remark 2, we can reduce GAGA 3 to X equal to the projective space. In fact, if we have X inside the projective space, given by some I, and G is analytic, coherent over X, then the push forward is analytic coherent over Pn. And so we know by GAGA 3 that it will be the same thing as some F tilde n, where F tilde is algebraic coherent over Pn. But what we want to see is that, what we have to see is that this F tilde is in fact defined over X, right? This is exactly the same thing as showing that when you take the sheaf of ideals of X times this sheaf F tilde, this has to be 0. Okay, and how do you see this? Since when you take the analytification of this will be exactly analytification of the sheaf of ideal times I push forward of G, and you know that this is 0 since G is supported in X, right? And so since this is coherent, the same argument that we gave before implies that this is 0, right? And so this F tilde comes from is equal to the I push forward of some F coherent. algebraic over X. Okay, and obviously the analytification of F will be the analytification. Will be G, right? Okay, so we have reduced the proof to the projective space, and we just need to check the existence, not the uniqueness. The time. Okay, so proof. Okay, so the claim, we have to do several claims. Claim 1. So let Pn minus 1 inside Pn so be a hyperplane section given by L equal to 0, a linear equation. So then for every okay, so sorry, here before putting the claim, so we will proceed by induction on the dimension, on n. Okay, so the claim is that if we take any hyperplane, then for every analytic coherent sheaf, A over Pn minus 1, we have that the cohomologies are 0 for every q bigger than 0 and for every m bigger or equal than some m0. Okay, this is the first claim, and this is clear because since by induction hypothesis we are assuming that GAGA 3 is true, right? So by induction hypothesis we know that this A is equal to the analytification of some B for B algebraic coherent. So we know that this AM is exactly BM N, and the result follows by Serre's theorem. Okay, and the claim follows by Serre's theorem applied to B. And GAGA 1. Okay, so this is Cartan B. Cartan B for one dimension less. So the claim 2 is Cartan A. So let M be any analytic coherent shift now over Pn. Then there exists some number m0 depending only on the sheaf, such that for every m bigger or equal than this number, and for every x in x, this x is globally generated. Okay, so you understand what I mean by globally generated by the global sections. Okay. Okay, so this is cartan A. So note that okay, so if H0 of Pn mm generates mm of x, then I mean, if it's generated for m0, then this is globally generated for every m bigger or equal than m0. Okay, so it's enough just to prove it for one m0, and also if this happens, this is also true, and also m0 of y is globally generated for every y in some b neighborhood of x. This is Ioka's theorem, right? And so since x is compact, this claim is reduced to the following claim. Claim 3, for every x in x, there exists some number such that for every, well, such that mmx is globally generated. Okay. Okay, so, well, x is P. Okay, so why is this true? So consider the exact sequence associated to the hyperplane. Okay, and so tensoring it by m, we will get, well, analytification, analytifying it, and tensoring it by m, we have a sequence of this form. Right, where these two sheaves C and B are defined over Pn minus 1, right? C is the kernel of this map. So by definition, it is defined over Pn minus 1. Okay, we have this sequence, and so we can divide this sequence into two short exact sequences. So we have here Lm, mm, b0, and 0, c, m. Well, I am twisting it first. Here is m minus 1 and Lm 0. Okay, we have these two short exact sequences, and so we have the following diagrams. I mean the following exact sequences. So H1 of Pn m minus 1 to H1 of Pn Lm H2 Pn Cm, and here we also have H1 of Pn Lm to H1 of Pn mm, H1 of Pn Bm. Okay, we have these two sequences. Okay, so by claim 1, we have that for m big enough, these two things are 0, right? The Bm is 0, and the H2 of Pn of C is 0. This is since both sheaves are defined over Pn minus 1, right? So this is true for every m bigger or equal than some m0. Okay, and so in particular what we get is that the dimension of the H1 of m minus 1 is bigger or equal than the dimension of H1 of Lm, and this is bigger or equal than the dimension of H1 of mm, right? For every m bigger or equal than m0, right? This follows from these two sequences. And so in particular, since these are finite dimensional vector spaces, this is Cartan-Serre. By Cartan-Serre theorem, we know that at some point it will stabilize, right? So there exists some m1 such that for every m bigger or equal than m1, we have that the following map is an isomorphism: H1 of Pn Lm to H1 of Pn mm is an isomorphism, right? And in particular, we will have that for all these cases, the map that goes from H0 of Pn mm to H0 of Pn Bm is surjective. Right? Okay, so you're following? Right? Okay, so by induction hypothesis, we know that B is the analytification of some algebraic coherent sheaf F, right? Since this is GAGA 3. Okay, and so the global sections, right, the H0 of Bm is equal to the global sections of right? And by Serre's theorem, we know that this is also 0. No, this will generate. I mean, so by Serre's theorem, I mean the analogous theorem in the algebraic side of Cartan A theorem, this space H0 of Pn Fm generate Fm x for every m bigger or equal to some m2. Okay. Okay. And so let n inside mmx be the submodule globally generated, right? Generated by the global sections. Okay, so what we know is that the global sections will generate a Bm of x, right? So we already know that the global sections generate that n generates Bmx, right, for every m bigger or equal than m2, where this Bmx is exactly mmx tensor with the structure sheaf of the hyperplane, right? This is Pnx over the equation defining the hyperplane. Okay, and this is exactly mmx over the submodule generated by L in mmx. Okay, so since n generates this module, this is exactly the same. Well, this implies that mmx is equal to n plus the submodule generated by L. Right? And so we have that if we take the quotient, no, by n, yeah, by n, this will be exactly this. Right? So this is an ideal of the local ring. This is our finally generated modules, and we have this relation. So Nakayama's lemma implies that this is 0, and so we're done. Okay, so this proves Cartan A theorem. This proves claim 3, which implies claim 2. Okay, so finally the proof of the GAGA 3. So finally, finally, so by claim 2, this is Cartan A, We know that we can write G. G is the analytic coherent shift. We want to prove that it comes from something algebraic. So we can write it as a quotient of some twisting of some finite direct sum of twisting shifts. I don't know, H. Okay, we can write it like this. Well, in fact, we can have here another, well, some L where L is also a finite direct sum. Well, I will write it like this. L1, L2, where L1 and L2 are finite direct sums of twisting shifts. Well, analytified. Okay. So we can write it like this, and so by GAGA 2. So let's call this map G. So by GAGA 2, there exists some F. So let's say that this is L1 and L2 and. So this is these are twisting shifts in the algebraic side. By GAGA 2, there exists some morphism F from L1 to L2 such that Fn is equal to G. And if you take the cokernel of this morphism F, you will have that the analytification will remain exact. And so Fn is isomorphic to G. This is the proof. Okay, is it clear? Okay, so the last comment I want to do is a corollary of this theorem. This is Chow's theorem. So every analytic subvariety of the projective space is algebraic. And the proof is very simple. So let Y be an analytic subvariety of Pn. Now we know that the E star of OI is analytic coherent over Pn. This is Oca's theorem and Cartan's theorem. And so by GAGA 3, we know that it is the analytification of some sheaf Fn, right? For some F algebraic. Right? And so in particular, the support of F is equal to the support of OY, so it's equal to Y, right? But the support of an algebraic sheaf is always algebraic. So this implies that E is Zariski closed. Okay. Well.
What is projective, right? When you mean analytic is closed.
Yeah, analytic closed subvariate. Yes. Okay. Clear? Questions? More questions?